there seems to be a window of superconductivity that exists for band filling or for number of extra electrons. On the other hand, this is one necessary but not sufficient condition. A second necessary but not sufficient condition is you have to suppress this transition enough. If we suppress it slowly, as is the case with copper when plotted against extra electrons, we miss this window of extra electrons that support superconductivity. So operationally, we have two necessary conditions. We have to have an extra electron count within this window, and we need to suppress these upper transitions adequately. Now, this is not unique to just transition metal doping of the 1,2,2s. You see very similar phase diagrams, for example, fluorine doping of the 1,1,1s. And it's not only associated with doping. If you apply hydrostatic pressure, for example, to barium iron 2 arsenic 2 and suppress these upper transitions, you can induce superconductivity as well. So one of the questions is, how are these different perturbations affecting this material and what's governing this superconductivity? I believe it has to do with essentially preserving enough magnetic fluctuations to allow the superconductivity to use that to create the group of pairs. All right. In addition to a substantial TC, HC2 is looking very promising as well. Here's high magnetic field measurements on potassium-doped barium iron 2 arsenic 2 we were able to do at the National High Magnetic Field Laboratory. It's fairly isotropic, but even more importantly, at 20 Kelvin, this lower HC2 is above 40 Tesla. At 20 Kelvin, we have 40 Tesla. That's phenomenal. If JC can be made large enough, these will be technological materials. That is not a trivial if-then statement. JC is often the deal breaker for applied superconductors. So that will be a focus of great research in the coming years. Now, this is not unique to the 1,2,2s. Here's some data coming out of a collaboration with David Larkin-Mastier, Alex Gurevich, and others at the Magnet Lab. They looked at a fluorine-doped neodymium 1111. Here's the data with different criteria. The data are the solid dots here. The black and blue lines are various theoretical extrapolations. We can forget the theory if we look just at the data. Again, the lower HC2 is in excess of 40 Tesla at 20 Kelvin. These look promising. Now, the nature and mechanism of superconductivity in these materials is still being debated. The proximity to structural and magnetic phase transitions make either of these promising candidates for what's mediating the superconductivity. My prejudice is the magnetism is definitely playing a role, but that still needs to be borne out fully. So, let me start backing out of this talk. First iron arsenides, and then a wider view. Iron arsenides, there are a bunch of questions. There are operational and empirical questions. Is iron special, or can we generalize to other transition metals? More importantly, is arsenic special, or can I generalize, please, to antimony? Something that's not toxic, not volatile, and lovely to deal with. Those are very important questions, and we're trying to figure that out. Secondly, are we stuck with TCs below 60 Kelvin, or if we go to planes and chains or something like that, might we get 100 Kelvin? Now, physical questions. What's the symmetry of the gap? Ruslan was talking about that in the talk just before this. We'll hear lots of talks here. In addition, might it be different for the 111, 122s, or the 11s, or is it going to be the same type of gap in all cases? In addition, what's the mechanism? Is it important to being close to antiferromagnetism, to the structural, to both, to neither? There's a large magnetoelastic coupling. I suspect that's going to be important. Engineering questions: can powder and tube wires be made easily, and can JC be pushed up? Now, let's take a broader view. If we think of the past couple decades, we have been shedding or destroying prejudices. Okay? With the discovery of high TC, we got rid of the prejudice that oxides are irrelevant. Some of you are old enough to remember long ago, no one would look at oxides. That's clearly not the realm of superconductivity. Well, the high TCs killed that prejudice. Boral carbides got rid of the prejudice that superconductivity in intermetallics was dead. MgP2 got rid of the prejudice that you would never exceed 30 Kelvin. And, perhaps more importantly, got rid of the prejudice that density of states is vital for high TC. It is not. More recent work on the iron arsenides got rid of the prejudice that really high TCs were only the purview of copper oxides. Now, let's be more optimistic. There's one prejudice that seems to survive, which is extreme superconductivity. High temperatures is found near and often in competition with other phase transitions. The high TCs, you're competing with copper-based magnetism. Fluorocarbides and MgB2 are competing with structural phase transitions. And the arsenides seem to be competing with both structure and magnetism. Let's try to see what we've learned. With high TCs, fluorocarbides, MgB2, and now the iron arsenides, we're seeing that compounds that live between ionic insulators and broadband metals are the materials that offer interesting and potentially useful superconductivity. The materials that we're seeing this in are the materials that allow us to transverse or to go from these extremes, and this is beautifully summarized in the cacalcinides and pnictides. Often we can get our large characteristic frequencies with light elements that are either refractory, volatile, or reactive, and we can tune our band filling with alkali and alkali earth. Now, these circle regions are exactly the regions that the physicists have wanted to avoid, because these are painful regions to do your synthetic work and to characterize your materials. Chemists have lived here for a long time. Now, I think that what we need to do is focus on these materials. So, combination of these and often transition metals, not necessarily for density of states, but possibly for magnetism. So, I think we're going to have new searches in these poorly explored phase spaces in the next decade. And I would like to say to students as well as the older researchers, I think this is a phenomenally exciting time for superconductivity. We've had a series of discoveries, and I think perhaps the iron arsenides will let us understand and look back at the copper oxides and maybe even solve the high TC problem. But with searches in this phase space, the possibility of finding a isotropic or near isotropic material with a TC near 100 Kelvin, something that you can make wires and devices cheaply from, is becoming increasingly more promising. So, neat and interesting times. And with that, I'll say thank you, and that's it.
Okay, thank you very much.
Dr. Canfield, I thank you very much for this really interesting and refreshing talk. And I open the session for questions.
Keller, University of Zurich. Are you aware, is there any indication that there is a residual phase in the iron-based superconductors?
Well, I hope my colleague Makari Tanatar will discuss that in depth. This is something that's still being debated, okay? I think Makari has a strong belief that there's absolutely a pseudo-gap phase. I'm a little more guarded in my assessment of that. I don't know if even that vocabulary is appropriate to the iron arsenide materials. But this is something that's being debated in the field. It's an obvious analogy to the high TCs, but whether this analogy has physical meaning or not, I think we'll have to figure that out. It's a good question, and I think it's going to take a couple years of research to really address that. But come to Makari's talk, because he's a believer.
Thank you. Other questions? Yeah, there.
Okay.
The transition temperature is predominantly dependent on the energy of the excitation, that is to be exchanged between the participating electrons or holes, and the coupling parameter, that means the density of state at Fermi level and the matrix element of the two. Now, is it not possible to push the energy level to the highest density of state by the kind of pressure or any other mechanism of doping and the metallurgy and material science that is at command, especially in your laboratory?
Well, we have to be a little modest about what we can do. We have to work within the boundaries that nature allows us. Okay? Yours was a very theoretical question that presumes we know what excitation is forming as the coupling between the electrons that form the Cooper pair. Currently, my guess would be in the iron arsenides, it's a magnetic fluctuation, but we still don't know. Now, in terms of trying to increase the TC, basically my feeling is if you can suppress the structural and magnetic phase transitions even more rapidly than cobalt doping, you can remove this transition that will consume the fluctuations and have TC rise to maybe about 45, 50 Kelvin. Now, more broadly than that, to address the question, is there 100 Kelvin iron arsenide superconducting working somewhere? We have to find the structure that might allow that, and as of yet, that's not been found. But we still don't know what the mechanism for the pairing is, so we can't really answer the question you asked, which was, a Hamiltonian-based question. We still don't know what the parameters in the Hamiltonian are.
Thank you. Now our last question, please.
Thank you.
Because to react with the magnesium to get the MgB2, carbon requires a higher reaction temperature. A higher reaction temperature leads to larger grains, and larger grains lead to a lower JC. The trick for MgB2 currently looks to have as small grains as possible because it's grain boundary pinning that's giving rise to JC. So there's an optimization problem between wanting to have some carbon and give good HC2, plus finding the exact right size and temperature to avoid large grain growth. So that's operationally the problem, and you want to actually do this ultimately in situ in a powder and tube situation. So my colleague Doug Finnemore and many other people perhaps talking at this conference will be discussing some of the details of that. You bet.
Thank you very much.
Great.
I would like to thank the speaker and also the...
Oh, thank you very much.
You name it here.
Yes, it is.
Well, thank you very much. Thank you.